This is the general outline of how the system functions, or how the experiment has been conducted. So the method for actually carrying this out has been to design a track, which you can see here. We have two starting blocks for the robots. And the leading robot is teleoperated by a user, and the user guides this around the track over the finish line. And so the following robot will track the robot and follow it around the course. We've created a challenging track here with several different characteristics. You can see the corners here, T1, T2 and T3. They all have different curvatures to put the robot through slightly different situations. Now the reason for actually using a track is that the experiment is repeatable. We can follow the same line again and again. So from this setup, this method of conducting an experiment, we're able to compute the performance of the system by recording results. So this is how the experiment has been set up. I'm now going to present to you a video of the experiment. So here you can see the following robot in the distance, following the leading robot, and the pink ball on top of the leading robot at the front. It's a bit of a short video. So that was an example of a run. I'm now going to show you the results we've recorded from that run, how we've interpreted those to what they mean. The key points I'm going to talk to you about are the performance. Performance was good in a straight line, and also some problems with the actual design of the track as well. So here we can see the parsed readings from the laser for a single run of the experiment. So across the bottom here we have the number of measurements taken, and across the top here we have the distance error. So this is the error from the set point, so how far it varies from the 1 meter. So to begin with here we can see a constant line where there's very little change between in error. So it's maintaining a distance of about 1 meter from the vehicle. It then loses this slightly here, this blip, retains it, and then it loses it again throughout the run up to the top point here. The reason for this is as the robot's going around the track, it's unable to, the locomotion of the robot reduces the speed of the robot as well. It uses a skid steer mechanism. At this point here, at the top point here, it's able to then reduce the error back down to almost zero. The reason for this is because of the design of the track. As the leading robot exits the second corner, it's actually quite close to the following robot. So if I can move back a few slides. So as the leading robot exits the corner here, the following robot actually spots it and starts to track it across here, so it cuts the corner. So it's kind of cheating, it regains ground again, reduces the error. So that's why on this graph the error reduces down to here. So as it carries on around the track, the error starts to creep up again. So this is an example of an experimental run. I've performed some statistical analysis of the runs that we conducted. Unfortunately, we only conducted 17 runs before we suffered a hardware failure on one of the robots, and so we couldn't do any more. But I've plotted here the root mean square error, a histogram of the root mean square error for the runs. From this graph, it's possible to see that there is not a normal distribution of the data So therefore, we can only conduct non-parametric statistics. We would conduct the Mann-Whitney-Wilcoxon test if we were to compare this controller against another implementation, so ideally another controller. If we were to compare any more, we'd use the Kruskal-Wallis test method. So this is shows you how the system can be used to compare against other controllers as well. So finally, from conducting the experiments and designing the system, I've drawn some conclusions from this work. I've successfully integrated three relatively large topics, that is vision, robotics and fuzzy logic. And that is to produce autonomous vehicle following of robots. So they are able to follow robots. And they've done this in an unstructured environment as well. So they've actually tested it in several places, inside buildings and outdoors as well. So from the results that we've seen, it's possible if we can collect some more results and improve the system slightly, so a bit more tuning, tweaking is required. We can conduct a comparative analysis against other types of controllers. So this is what I've concluded from this work. To extend this work further, I'd like to use non-stationary fuzzy sets to produce a controller. This hasn't been done before. The idea behind non-stationary fuzzy sets is that it models the variation that humans make when making decisions. So to represent this in a non-stationary fuzzy set, you would have a perturbation function which changes the membership function slightly. Inferences are performed on these outputs, and the outputs are aggregated together. So a single control movement using this type of controller would consist of several inferences which are then aggregated and totaled. This is then used as the output. And so it combines different decisions, if you like, variations in this. So I'd like to experiment with a controller using this method. This is an outline of a non-stationary fuzzy set system. So it's very similar to stationary systems. Instead, the inference is performed several times, n times, and then the final output is aggregated here into a crisp output. So that's the idea behind the non-stationary fuzzy set system. We'd like to explore that idea further by applying it to control. So this concludes the presentation. I'll put some links here for some sources of information. I've got several videos on the CCI's area on YouTube. I've also maintained a blog throughout the project as well, all the trials and tribulations of the work, and that's accessible online. And also the news article mentioned earlier about the autonomous fleet of taxis in Daventry. I found the link for that online as well. If anyone has any questions or would like to contact me, it's my email address there. I'd like to thank both my supervisors for this work, Dr. Simon Coupland and Dr. Shangming Zhu, and also Professor Andrew Hugel of the Institute of Creative Technologies. Provided a bursary for me to do this course, and also provided me with a laptop as well to try the course. And also Dr. James Wheeler, who's helped with hardware issues and technical problems throughout the work as well. Thank you. Would anyone like to ask any questions?
Thanks, Steve.